All right, gas laws. Boyle's Law. We're going to go through a bunch of nerdy scientists. They developed these laws pertaining to gas, pressure, volume, temperature. They each have their own law. The law gets combined, and then we're done for the day. So the first nerd is Boyle. He developed this law that says the volume of a given mass of gas varies inversely with the pressure when the temperature is kept constant. Inverse means when something goes up, the other thing goes down. Nailed it. Yeah, I'll put it up on the screen. All right. His formula is P times V, P for pressure, V for volume, equals K. K is a constant for a given sample of gas and depends only on the amount of gas. We really don't actually do much with that because we do it in terms of a ratio, such as P1 V1 equals P2 times V2. So when comparing the same gas at different pressures and temperatures is when this formula comes in handy. So much like this first sample problem. With these problems, the only thing you need to make sure of is that your pressures are in the same units and your volumes are in the same units. It doesn't really matter what the units are as long as they are the same. So when a certain sample of oxygen is placed into a 425 milliliter container, its pressure is equal to 387 kilopascals. The gas is allowed to expand into a 1.75 liter container. Calculate the new pressure of the gas. So our initial volume, V1, is the 425 milliliters. Its first initial pressure is 387 kilopascals. I would say those should be our goal units for P2, V2. Our second volume is 1.75 liters, but like I said, we need to have the units be same. 1750 milliliters. Good. If you needed to do railroad tracks on that one, you are more than welcome to. And then we need to calculate our second pressure. So the formula is P1 V1 equals P2 V2. Plug it in and solve. So first pressure is 387. Our first volume is 425 equals our second pressure, we don't know, and 1,750 milliliters. Do you need me to do the algebra to solve for P2? Yes. All right. So first step, multiply 387 times 425, and you should get 387 times 425. 164475 equals P2 times 1750. To get P2 by itself, we have to divide the 1750. Cancels on that side. What you do to one side, you need to do to both. So P2 will equal the what is it, quotient of that division right there. And second volume is 93.99 kilopascals. All right, second nerd on tap today is Charles. He said the volume of a given gas varies directly with the temperature of the gas. So that means when one goes up, say temperature goes up, what will happen to the volume of that gas? It will also go up. What one does, the other one does. So here's his original formula, but again, we usually use it when we compare two different scenarios. So we will set up the V1 over T1 equals V2 over T2. With this, we must convert all of our temperatures into kelvins. It's a simple process. You simply take your degrees Celsius temperature and add it to 273. So, practicing that, a balloon is filled up to a volume of 2.2 liters at a temperature of 22 degrees Celsius. The balloon is then heated to a temperature of 71 degrees Celsius. Find the new volume. So our initial volume, our V1, is 2.20 liters. Our initial temperature is 22 degrees Celsius, but we have to convert that into Kelvin. We do that by adding 273 to it, and we get 295 Kelvin. Our second volume, we do not know. And our second temperature is given as 71 degrees Celsius. Convert that to Kelvin by adding 273, and you'll get 344 Kelvin. Then we can use Charles' law that says V1 over T1 equals V2 over T2. And then plug in what you know. 2.2 over 295 equals V2 over 344, and then solve for V2. I would use cross multiplication on this setup. You could do the algebra, that's fine, but it's basically the same. So you take the corners, multiply them together, 2.2 times 344, and then you go these two opposites, 295 times V2, and then what is that? 2.2 times 344, 756.8 equals 295 times V2. How do you get V2 by itself? By 295. That cancels out. Divide 295. V2 equals 2.57. What's our unit on that volume? Liters. Very good. All right, next scientist is Gay-Lussac's. He said the pressure of a given mass of the gas varies directly with the absolute temperature of the gas when the volume is kept constant. So here is our comparing formula. Again, your temperature needs to be in Kelvin. Why don't you guys go ahead and work this problem out, see that you can set these up correctly. All right, what are we getting here for your pressures? Cora?
11.26 ATM.
Any dissent on that? You rounded differently, that's fine. Do you need me to go over this, anybody? Are we good with these? Seth? Caitlin? Yep. All right, the combined gas law then takes all three of those that we've just talked about and combines it into one handy-dandy tool for us to use. So the only little snag here is you need to remember your order of operations and multiply your pressure and volume together before you do the division. So we can go ahead. I'll do this one with you since I didn't do the last one. Initial pressure looks like 0.833 atmosphere. Initial volume is 2 liters, and temperature one is 35. What do we need to do to that 35? 273. And we get, is it 35? Yeah. 308, yep, thank you. Then it is brought to standard temperature and pressure. What will be the new volume? So we don't know the new volume. What is standard pressure in atmospheres?
6.02
Nope, simpler than that. Oh, close.
0.
One atmosphere is standard pressure, and your standard temperature, 273. You should probably memorize standard temperature and pressure. 1 atmosphere and 273 Kelvin. So So then we set up our formula, P1 times V1, so 0.833 times 2 all over 308 equals 1 atmosphere times V2. So we can really just say over V2 because that looks nicer, divided by 273. I would cross multiply this one again. So 0.833 times 2 times 273 equals 308 V2 divided by 308. And your second volume should be
The V2 looks a lot like 1/2.
Oh, I see it, yeah. Do you want me to fix it, Studi?
I like it that way.
1.48 atmospheres. Are you gonna play basketball next year if it's combined, or when it combines?
Yeah. Can't give it up now.
Is it gonna be over there?
Apparently, we're gonna do like half and half everything. That's what Mr. Raymond said.
That's finalized, isn't it? Not maybe the scheduling, but
I think so.
the pairing.
Yeah.
I think Klingfist was asking me about that yesterday. Oh, total side conversation in the notes. Sorry, guys. Forgot to pause it. All right. The last one is Avogadro's law. This is the volume of a gas is directly proportional to the number of moles of the gas when the temperature and pressure are held constant. Again, we have one of our little handy dandy formulas. Do you want to do the problem? Yes? All right. So a balloon has been filled to a volume of 1.90 liters, and it has 0.0920 moles of helium gas. If we add another 0.021 moles, what will be the new volume? So V1 over N1 equals V2 over N2. Initial volume 1.9 over 0. Oh wait, our second volume is plus 0.0920 because we added the 0.021 moles. Does that make sense? Why we have to do that addition? Because it says an additional 0.021 moles were added to the original 0.09. Okay? So N1 is still 0.0920. Our second volume we don't know, and so we need to do this quick addition. 0.31. So 0.113. Cross multiply, and it'll be 1.9 times 0.113 over 0.092. And your second volume should be 2.33 liters.